Hello everyone and welcome to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. I thought of doing a video about certain subtleties of the very well-known linear voltage regulators like LM317, 337, 117, 217, stuff like that. Also, a few, or I should say one subtlety about LM78L something and 79L something, those fixed voltage regulators that come in a transistor package and typically give a fixed voltage, at least in theory, at least the way they are designed originally to be used. I don't see quite often on the internet these things, and I was inspired by someone who is currently trying to build a power supply. So perhaps these informations will be something new to you and you will find them useful as well. It's not much philosophy, it's not rocket science, so we will just go to the workbench and I will explain all the things that I want over there. Okay, so these are pretty well-known voltage regulators, linear voltage regulators, and in their simplest forms, let's talk first about LM317, 217, 117, and also this applies to the variants with 3 in the middle, like 337 and so on. These with 1 in the middle are positive regulators, the ones with 3 in the middle are negative voltage regulators. So this is the absolute simplest schematic that can be used to obtain an output, a stabilized output voltage, and it's very well known by everyone who has worked with these circuits, and there are plenty of tutorials on the internet, especially in English, about using this IC with these two feedback resistors on the output, one between the output and the adjustment pin, and one between the adjustment pin and the ground. What is not so well known and not so many people mention this detail, although it is important, is the fact that the IC needs a minimum current in order to work, a minimum current for on the output in order to work. So it basically needs a minimum load, right? Now this minimum load can be achieved by only these resistors, but we do need to take care of what values we give them, and this is actually specified in the datasheet. We see at some point minimum load current. They tell us that it's typical 3.5 milliamps. We don't know how the minimum is. Perhaps it doesn't exist, and it can be up to 10 milliamps. So again, we're talking about the minimum load current, which varies between some values in a range, right? So worst case scenario, we will have to provide 10 milliamps to our LM317 in order for it to work, in order for him to work correctly. Okay, it's not always 10 milliamps. I will show you that in my case for a particular chip I need only 1 milliamp, so it's actually lower than the typical value. But if we are designing a circuit and we want to be able to duplicate that circuit as many times as possible without too much stress about it, we need to take care to take into consideration the absolute worst case scenario. And worst case scenario in this case is when we have 10 milliamps of minimum load and therefore minimum current passing through the stabilizing circuit. Now it's a bit difficult to understand from certain data sheets. They show you, like for instance, this is from ST Microelectronics. They show you the entire circuit, which is nice, but it's not so useful and it's not so clear why this minimum current even exists in the first place. But if we go to Texas Instruments and we take a look at the same LM317 datasheet, we see that they are actually making a simplification. They, when they show us the functional block diagram, they don't show us the whole circuit. They show us a simplification, and in this particular case, it is actually a lot more useful than the previous datasheet. Okay, so in their simplification, we see, we can turn it like this, so we have input on the left, output on the right, adjustment on the bottom. We see that we have a Darlington pair between the input and the output. Nothing weird about that, but we have an op-amp that is controlling this Darlington pair. It's opening or closing it, and the op-amp of course needs to be powered by some voltage and some current. And well, guess what? Its power, so if we take a look like this, the positive rail of the power supply of the op-amp is the input pin, and the negative rail is the output pin. Okay, so this is the reason why we need a minimum load current, because the load current is at the same time the current that passes through this op-amp in order for it to work correctly. Okay, it's not that current doesn't passes through completely through the op-amp. Actually, a small fraction of it passes, but the problem is the op-amp needs a minimum voltage, and that minimum voltage, minimum power supply voltage, cannot be achieved if the current is just too low. Okay, and that's the reason why we need a minimum load on the output. It has nothing to do with the adjustment pin current, which is specified because the IC is generating a current for this Zener diode, and obviously it's passing it on the output, on the adjustment pin, but that current has nothing to do with the minimum load current necessary. Okay, so now we know from before that we need to put these two resistors usually, and between pin output and adjust, the IC keeps a reference voltage of approximately 1.2 volts. Okay, so in order for us to have the minimum voltage, the minimum current given to this IC, we can do that by just setting these resistors correctly. Now these resistors also determine the output voltage, but we can use the fact that between the adjust and the output pin are there's just a 1.2 volts constant voltage, and we can divide that by the minimum current that we need, which is 10 milliamps. Okay, in order for us to figure out that we need R1 in this particular case to be a maximum of 120 ohms in order to accommodate for the absolute worst case scenario. Okay, that does not mean that R1 needs to be 120 ohms or less. The IC can actually work with some ICs can actually work with these resistors a bit higher, like 220 ohms, 270 ohms. That's because those particular ICs don't really require 10 milliamps. They require a lot less. However, that is the particular logic behind choosing the value of R1. And of course, R2 is chosen based on R1 and that special formula that I'm not gonna show here because everyone knows it, or if not, you can go search one of those basic LM317's tutorial videos. In order, that formula gives the output voltage, and it's in function of R2 and R1. But what's important is for you to understand, you know, why and how to calculate R1. So, in order to better understand this situation, let's do a bit of an experiment. And I've prepared, just give me a minute to see, to find that particular page. We will make a circuit on a breadboard, and so this is the standard circuit, the classical minimal circuit in order for LM317 to work and to have an output voltage. But we're going to remove this potentiometer. We're going to consider that we have turned down its value all the way to the ground, all the way until it is 0 ohms. In this case, it's as if the adjustment pin is connected straight to the ground, like here, and the resistor between the adjustment and the output is now connected straight to the ground because the adjustment is connected to the ground. And we're going to put an ampermeter in series with this resistor, and this resistor is actually variable. In my case, it's a 25 kilo ohm resistor. And we're going to monitor, I'm going to put 15 volts on the input, and we're going to monitor the output voltage so that, and the current through this resistor, so that we can see what is, for this particular IC on my breadboard, what is the absolute minimum current that I need to provide him in order for me to have a stabilized 1.2 volts on the output. Because when we are connecting our adjustment pin to the ground, on the output we will have exactly this reference voltage, which is 1.2 volts, or at least this is how it should be. Okay, so this is the ampermeter. Okay, I have 15 volts on the input. I have the semi-adjustable, which right now is not connected at all. And I have, instead of having 1.2 volts on the output, I have 8.4 volts, okay? Because the current is so small that that internal op-amp cannot work, so LM317 cannot properly regulate. So, like I said, this semi-adjustable is 25 kilo ohms big. I'm going to connect it, and it's now set to the maximum value. We are creating 270 microamps of current in our circuit, and we see that the LM is somewhat starting to work a little bit better. It dropped its voltage from 8 point whatever it was before to 6.5. So now we're going to decrease the value of this resistor, which will increase the value of the current, and we will take a look at how the IC will do a better job at regulating the output voltage. Okay, remember, we need to reach 1.2 volts on the output. Until then, the IC does not work correctly. So at 400 microamps, this particular IC that I have here gives me 5.5 volts. It's still not good enough. At 500 microamps, 4.6 volts. And we keep increasing it until we get to about I think I went, okay, I went a bit too fast. Let me take it down. Okay, so at about 900 microamps we are very close to the reference voltage, so we are very close to the IC working correctly at all times. And if we increase it a little bit, we now see the reference voltage now at 1 milliamp of current. The IC is starting to work correctly, and it's starting to do proper job. Okay, we can further increase the current, but the output voltage will stay because, well, it doesn't really matter all that much. Okay, and I'm not gonna go too much increasing the current because it's very easy for me to do a short circuit here with this particular semi-adjustable. So as you can see, in this case I need just 1 milliamp of current in order for my LM to work properly. It's less than the 3.5 that's typical in the data sheet, but we cannot really rely on the fact that every LM317 that we are putting our hands on will need just 1 milliamp of current. Okay, we need to calculate for the worst case scenario, and that is 10 milliamps, 10 times more than this. Okay, at 1 milliamps that R1 resistor could be as high as basically 1.2 kilo ohms, right? But we cannot really have that in order to be assured that this works correctly at all times. Okay, now I hope you understood why that need for the minimum current is, and now let me show you a trick that not so many people know, and that is the fact that these two resistors here are actually optional. And I'm not sure, I haven't looked on the whole data sheet. I'm not sure if they are actually showing an example where these resistors don't exist anymore, but the idea is that these resistors are not the only way to set the output voltage. Okay, actually there's another way which we might find more useful in some cases, and that is, ignore this Arduino thing for the moment. Okay, we have 15 volt, we have the input voltage going into an LM317 in my example, and we don't have those resistors at all. We have a voltage supply, which in my case is just a 9-volt battery, connected from the ground to the adjustment pin, and also on the output we have a minimum load, which in my case is just a resistor with a LED that shines green in my case, in order to have that minimum load current necessary for it to work. Okay, so the output voltage in this case will be the voltage of this voltage source plus the 1.2 volts reference of the LM. Okay, and this is particularly useful if you want to build a power supply that's I don't know, a bit more fancy, we might call it, and you want to control it digitally somehow. You might take something like an Arduino and to give a signal to a DAC. Okay, a DAC is a digital to analog converter, in order for the DAC to generate a voltage. Okay, and that voltage you can then feed into of course a voltage with respect to the ground you can feed into the adjustment pin of an LM317 or anything else like that, and essentially you are setting the output voltage of the whole regulator to be that voltage from the DAC plus the 1.2 volts reference. Okay, this is something that not a lot of people know that it is possible. So let me change a bit the setup here and show it to you so you can better understand this concept. So I have a 9-volt battery, which happens to be brand new, and I will connect it between the ground. I will connect the minus of it, okay, to the ground, and the plus to the adjustment pin of the regulator. Okay, we will also be monitoring, although, well, the voltage of this does not get to be changed, but anyhow, we are going to take a look at the voltage of the battery on this multimeter, and also we will be connecting the output to this green LED that draws the minimum current from the output. And what do we see? We see that the voltage of the battery is about 9.7 volts because the battery is brand new, and the output voltage is 10.9 volts, which is 1.2 volts higher than this, exactly like I said. So we have made the LM317 to give on its output the voltage of the battery, which is a reference voltage, an external reference voltage as far as he is concerned, plus the internal reference voltage of 1.2 volts. Okay, and if I were to adjust the voltage of the battery, then the output voltage would also go up and down. The only thing that we need to keep in mind is to have that minimum load current on the output of the LM317, because if we don't have it, like if I remove this, see, the LM317 has jumped all the way to 11.6 volts, which is more than it should have, okay, and it's also not reliable. So that was one trick that I wanted to show you, and that not so many people from the electronic community are showing. Another trick is related to the fixed voltage regulators, like from 78L series or 79L series. Okay, these are supposed to be positive voltage regulators with fixed values, and these fixed values they come embedded from the factory with each IC, and they come manufactured in various voltages. But the idea is that it is not impossible to make such a voltage regulator to have a different voltage output. Okay, so even though they specify it that it's a fixed voltage, and the way we would use it as a fixed voltage is very simple. It has an input pin, a ground, and an output pin. On the input pin and the ground, we are giving it a voltage, an input voltage, and on the output we have that particular voltage that is embedded in the chip. The numbers that come after the L state the voltage on the output. Okay, so 78L05 gives 5 volts on the output, 78L12 gives 2 volts on the output, and so on and so forth. But there's absolutely nothing stopping us from using a voltage divider on the output, just like with LM317, in order to have a stabilized output voltage higher than the one that is embedded on the chip. So we could use a 78L05, for example, to have anywhere between 5 volts and above of stabilized voltage on the output, of regulated voltage on the output. Okay, and I know it sounds weird, but it is possible. The only condition is that we take care of this particular condition, this particular requirement, similar to the minimum load current that exists for LM317, 337, and so on. From the same reasons, there is this quiescent current of about 6 milliamps maximum, and quiescent current change of about 1.5 milliamps, so about 7.5 milliamps in total maximum current that this integrated circuit needs in order to operate correctly. If and unlike the LM317 and 337, which takes its current from the input and output pins, 78 and 79 series take its current from the input pins. Okay, so it operates from the voltage on the input. In other words, the ground pin is important, and through the ground pin this current flows, not through the output pin like in LM317. So if we make sure that this IC has this minimum current at all times, meaning if we make sure that this resistor is not that big that this IC doesn't have enough current to work with, then we are happy and the IC is happy, and we get a different voltage on the output. We get it to work this way to provide a higher voltage. Okay, and the way I think of it is very simple. Obviously we need to see what's the maximum resistance value of this resistor. Well, the IC keeps its voltage. Let's say that it's an L05 into IC, right? So it gives 5 volts. Well, it gives this 5 volts between the ground pin and the output pin. So the trick works because we can raise the ground pin of the IC away from the ground pin of the rest of the circuit. Okay, so when we set this resistor and obviously this resistor later, we have to think about what's the voltage drop on this resistor, and that's going to be the voltage that we want minus the voltage of the IC. Okay, let's say that I want 10 volts. I'm going to feed it with 15 volts on the input. Let's say that I want a 10 volt total output voltage, and I'm going to use a 78L05, so it's going to have 5 volts here. Well, logic says that we're also going to have 5 volts here, and we need to have a 7.5 milliamp of current through this resistor. So it's just a matter of dividing 5 to 7.5 milliamps and seeing what the value is. It's something like 600 something ohms. So I chose a 560 ohm resistor because it's the nearest standard value. Okay, and because I theoretically want 10 volts here, which is double, then I'm also going to put a 560 ohm resistor here. Okay, and that should give me 10 volts. In reality, it doesn't really give me 10 volts. It doesn't really give me 10 volts because probably there are various... just a second to disconnect this battery. Okay. It doesn't exactly give me 10 volts because there can be differences between the resistors, because I'm using 5% you know, resistors, or I don't know, other factors, but it's definitely giving me more than 5 volts. Okay, so we see now a 12 volt voltage output from a 78L05. And if I were to have, if I were to want a smaller voltage, I could just remove this resistor with a smaller value, or this resistor with a higher value. Okay, it's easier for me right now to remove this with a smaller value. So I'm going to remove this 560 ohms, and I'm going to put a 150 ohms. Okay, between the ground and the ground of the IC, and here we go. We have 7 volts, less than 12, but still more than 5. This trick obviously cannot give you a voltage less than the one that the IC gives, but it's still useful enough, especially if it would be helpful for us to buy a lot of 78L05s and then not worry that we will need a 7 volts or a 9 volts or an 8 volts or an 11 or 12 or whatever other voltage. We can just have a whole bunch of 78L05s, and of course 79L05s for the negative voltages, because this trick works there as well. And then whenever we want higher voltages, we just put 2 more resistors like that, which don't occupy that much space on the circuit, and we can have whatever other voltage we want. Okay, including an adjustable one if we really want one from the fixed voltage regulator. Most of the times we will not want to have an adjustable one because it doesn't make sense. If we are using a fixed voltage regulator, we are we most likely want to power a specific circuit in a device which needs a fixed voltage, so we won't feel the need to adjust it, right? So these are pretty useful tricks, I would say, and I hope now you've learned something new that you didn't knew before. Hope you found it useful, and thanks a lot for watching. I intend to upload soon new videos about electronics, so keep in touch. If you would like, please click the subscribe and like button. Also, if you like what you see and you would like to support my work, please consider supporting me on Patreon. The faster I can buy components and devices, the faster I can learn new things, and then the faster I can come here on YouTube and teach you as well, so that you don't have to bother wasting time and energy figuring out these things on your own. Thank you very much for watching, and hope to see you soon next time. Bye bye.